Okay, so we're going to have, I think, some Lego and demonstrating how to build a model, I think. So, helping Tom.
Okay. Good. Hi, I'm Kelvin. Today I'm going to attempt something experimental. I'm going to try to deliver the group talk without PowerPoint, so I'm going to embrace the analog realm. Okay, so today I'm going to talk about developing automated methods to estimate spectrally resolved direct normal irradiance, DNI, for solar energy applications. The majority of the content of this talk comes from a paper draft that literally submitted it last week. Helen is looking at me right now. Just thank you for all the people who helped along the way. So to begin with, and obviously like mandatory branding requirements. Okay, so let's begin by talking about what is the state of the art in terms of solar technology these days. So obviously we see a lot of solar panels around, and most of these solar panels we see, in urban areas and rooftops, they're what we call single junction solar cells. And it's single because there's a single layer of semiconductor, typically that of silicon. And because there's only one layer, it usually has a relatively simple spectral response. So what's this shown here is demonstrating that. So the solid line here shows the typical ground irradiance spectrum, and the shaded region represents the theoretically capturable part of the solar spectrum. So you can see it's not very good. As a matter of fact, the typical efficiency for these things is only about 20%. Right? So obviously we can do much better than that. And the state of the art in terms of solar technology these days are what we call multi-junction solar cells. And this is a typical one. It's a commercially available triple junction solar cell. And each of this layer in the semiconductor is designed to absorb a very specific slice of the solar spectrum. And as a result, more of the solar spectrum can be utilized as a result. And the world record in terms of solar panel efficiency is done by one of these guys, is at 46%, so quite a substantial improvement over the single junction case. And to achieve such high efficiency in a commercially viable way and economical way, these multi-junction cells are typically topped with an optical concentrator, which is represented by that. So that means that unlike a typical silicon single junction cell, which can absorb solar radiation, diffuse solar radiation from all directions, these multi-junction cells topped with a concentrated system can only accept photons from a very specific direction. And that has implication, as we see later, to how we actually count up the number of photons that these devices can actually see. Okay, so the bottom line is that multi-junction cells, as you can see, has more complex, more nuanced spectral responses. Unfortunately, existing multi-junction cells are typically designed and rated and optimized with a standard solar spectrum. So this is a typical solar spectrum used within the photovoltaic community. It's from the American Society for Testing in Materials. It assumes, among other things, well, first of all, it's fixed, right? So independent of climatology, it's fixed. It assumes an air mass of 1.5 and a low aerosol optical background, which can be very unrepresentative of the actual climatology in which many of these solar panels are being deployed. Previous studies have shown that there can be up to if I can find the number, 75% deviation in the simulated energy yield between assuming this fixed spectrum and actually using a real solar spectrum when we estimate the power that's being generated by one of these guys. So moving forward, it's quite important for us to when we design multi-junction cells, to not use these fixed solar spectrum and instead use spectra that are based on real observations and real climatologies. And this is where we can come in. So the quantity that is of interest here is the direct normal irradiance. It is the irradiance projected in the normal direction, sort of pointing towards the sun. Right? And because these multi-junction cells has, as we saw, complex sort of spectral responses, we're not just interested in the broadband intensity. We want a spectrally resolved quantity. Now, unfortunately, ABC magnetic fridge pieces doesn't come with Greek letters, so I don't have lambda. So I'm going to use an inverted Y for that purpose. So that's what we want, DNI, spectrally resolved DNI. So the next question is, well, how we're going to, estimate these quantities. So let's just quickly outline what we can do and sort of identify the main things that we need to account for when we estimate these quantities. So here I have I've separated into 3 buckets. So first of all, it's important for us to understand, on the ground side, the instrument, right? So the spectral response, the optical tolerances of these things. Right? On the other hand, it's also important to know what we have on the top of the atmosphere to begin with, and that depends on geometry. So things like solar zenith angle, right? So how high the sun is with respect to the sensor. Also, it depends on how much the sun is producing, right? And we can model, sun-Earth distance and whatnot. But because we're going back in time, we have the benefit of using satellite measurements. So this is my best attempt at building SOURCE, which is a NASA satellite, solar radiation and climate experiment. It measures top of the atmosphere broadband irradiance. So that's what we're going to use in our product, like that. Okay, so top of the atmosphere, ground, and so the remaining question is everything in between the atmosphere part, right? So does anyone have any idea what's important? Any guess?
Are you going to put water over the top?
No, but I do have a water molecule. What else? Ed, what else?
Clouds?
Clouds, yes, clouds. Okay. And ozone, probably, and carbon dioxide and so on. But most importantly, actually, aerosol. And in this presentation, aerosols are going to be represented by 4x2 Lego bricks. Everything is within view. Okay, good. Okay, so that's kind of outlining the whole picture here, right? So, again, as far as the instrument is concerned, well, so that is fairly well accounted for. Geometry, we can just calculate it, that's fine. That we can just get it from a website, NASA's website, that's fine. CO2 doesn't really have any absorption bands, substantial ones in the shortwave regime, so that doesn't really matter. Cloud is quite important, but as far as solar farms are concerned, we usually we're primarily concerned about cloud-free, pristine, clear sky conditions. So as long as we do cloud screening beforehand, before we do, to estimate our DNI, that should be fine. Right? So that's the 3 things that remains, right? So ozone, water vapor, and aerosols. Yeah. So what I'm going to try to convince you right now is that actually ozone and water vapor are fairly well accounted for with existing analyses or reanalyses. So here, this is showing the ECMWF integrated forecasting system, and it's been shown that it can reproduce the total column ozone to within plus or minus 5%. Right. So this is what we've done is that we sort of simulated a standard atmosphere and we perturbed the ozone by plus or minus 5%. Right. Yeah, plus or minus 5%, and that is showing the impact it has on the spectral DNI. And the point is that you can't really see it, so it's quite small. Right. Water vapor has an uncertainty of plus or minus 8% from the IFS, and there's a little bit more impact on the DNI, but it's still relatively small when compared to aerosol. So these are all plotted on the same scale. Right? So this is again perturbing the different types of aerosol, holding everything fixed. And as you can see, by changing just the aerosol type, we get a very, very different spectral response, up to 150 milliwatt per meter square per nanometer. And as you can see, actually the main variation also occurs around the band gap region, which is most important as far as solar developing solar cells. So hopefully that convinces you that actually aerosol is the main thing that we need to account for in our when we estimate DNI. Okay, so that's kind of sketches out the problem. And before talking about the DNI estimation scheme, let's look at the site that we've picked to validate some of our schemes. So that would be Santiago, Chile. This is a map. Why Santiago, you ask? Because it has a complex aerosol climatology. So it's an urban industrial area. There's desert to the north, forests everywhere. Also the Pacific Ocean, which maritime dust, maritime type aerosols. Zooming in, A represents Aeronet. So this is an Aeronet site in Santiago, which is going to produce, which is where we're going to get our aerosol optical depth measurements. B is where we have broadband in situ measurements of the DNI. So we have actual measurements to validate our DNI estimation scheme. and C is the closest ECMWF grid point where we get, again, all our ozone and water vapor measurements. Looking at A here, the AeroNet size. So this is an AeroNet time series over 2014. So you can see there's wide variation in the aerosol optical depth, as well as the angstrom parameter, which is quantifying the spectral variation of AOD. The more instructive way to plot this is actually plot AOD against angstrom parameter, which is like that. So again, AOD against angstrom parameter. And that kind of qualitatively separates out different types of aerosol, because angstrom parameter is a proxy for aerosol size distribution. So fine type aerosol, coarse type aerosol. And AOD is a proxy for absorptivity. So very absorbing and less absorbing aerosol. So if we take a literature sort of classification scheme, we can kind of like start to see what are the climatological aerosol that is in Santiago. So mostly in the sort of clean maritime region, which is kind of expected because it's next to the Pacific Ocean. Okay, so the climatological aerosol is kind of maritime in nature, and that's going to be important later. Okay, so that's that. So let's start talking about the Dni estimation scheme. In this talk, I'm going to talk about 4 different schemes. All of them are based on radiative transfer calculation and sort of one building on top of each other, sort of counting for more and more factors and effects, and hopefully also improving the precision and accuracy in the estimated DNI. Okay, so for people who are not familiar with radiative transfer calculation, the way you do this is to build up an atmosphere, so specify all the species, density profile, and then run your radiation calculation through the layer of atmosphere. So let's build the atmosphere together, shall we? So let's begin from the ground. Right? Turns out, so this is ground plate. Turns out the ground albedo doesn't really affect the DNI because it's quite unlikely for photons to bounce off the ground and then backscattered into a very narrow optical sort of tolerance region. So it doesn't matter what we pick for the ground. I think I picked like 0.3 for the models and for the data you will see later. And then, so we build up the atmosphere, and we do that from a pillbox. So these are all the different sources that the model takes its data from. So we take carbon dioxide measurements from NOAA's Earth something something something. And then also we have ECMWF, which we talked about just now, like giving us information about the water vapor and ozone. Right. For other species, that doesn't really matter. We are taking just a standard atmospheric profile, that of a mid-latitude summer. So just other with this orange block. You can see it. Yeah. And for aerosols, so we've established just now that the climatological aerosol is sort of maritime clean type, right? So what we have done is that we've taken aerosol profiles from OPAC, which is a set of a library of pre-computed externally mixed aerosol components. So let's take a maritime clean. There we go. And above all, we have our solar measurements from our source. So there we go. So that represents our entire atmosphere. So just like for illustration purposes, let's say that is our estimated atmosphere. And let's say that is the reality, right? Okay, so that's a real thing, and that's the estimated. And just to make it more obvious which one is the real one, which is the estimated one, in statistics, you use a little caret symbol for like estimated quantity, right? So like E hat or P hat. So let's put a little hat on this estimated block. Okay. Okay. So this kind of represents our baseline because we have specified our aerosol from just climatological understanding of Santiago, right? So we call that the climatological aerosol scheme. Right? So that's our first scheme, right? And that will give us the baseline so to compare other schemes with, right? So you can see we're kind of getting the type sort of correct. The amount of aerosol is not quite right? So we can do something better, and that is the next scheme. So what we've done here is instead of just prescribing a priori a aerosol type, we run our simulation for all different types of opaque aerosol. So I think there are 10 of those, but there's no Legos are expensive, so I can't. So let's just say these are the ones. There we go. So maritime ones, continental one, urban one, dust, and another continental one, right? So the point here is that we are holding everything fixed. Right? So this is a typing process. We're trying to find a type of aerosol in the atmosphere, right? So and then we can just go and literally sort of compare them and find the right one, right? in practice, what we're doing is we sort of run these radiative transfer simulation, and then find the one that minimizes the root mean square error across all wavelengths. And in practice, I'm going to show you like actually what's happening here. Finally, some graphs here. So what we're showing here is the black dots are measurements from AeroNet, so i.e. kind of this block here, right? And then all these different lines are the result from all these different types of aerosol, right? Across all the wavelength, yeah. And here are the root mean square errors sort of sorted by order, right? So here we would have picked this maritime sort of tropical type aerosol. But regardless, because it's Lego world, we can just do it by visual inspection, and thus we will pick this one, right? Okay, so that will be our typing process. And that, we call it the spectral aerosol classification scheme, because now we're classifying the aerosol based on its spectral compatibility with the observation. Okay. So now we're getting closer to the observation, right? The amount of aerosol in the atmosphere is still, not quite right. So that is where the next scheme comes into place. And the idea is exactly the same. So now we have determined the type of the aerosol. We're going to perturb the amount in the atmosphere. So I'm going to represent this by having like this, right? So quite simple, right? And then we minimize the root mean square error, and then yeah, so it's quite obvious that would be the choice here, right? So let's pick that one, and that one I call it the spectral aerosol classification scheme with a load and optimization procedure. Yeah. So now we're getting quite close to the reality, right? But there's one more thing that we haven't considered, and I'm glad that Alex's talk just now is talking about sort of dust and showed a picture about with the sun sort of obscured by the dust, and what that is showing is actually circumsolar radiation. So just to go back to earlier in the talk, we were talking about these multi-junction cells are typically topped with a concentrated system. And these things have very narrow optical tolerances, right? So this is a picture of what it looks like. And the implication of that is that actually, besides the direct beam coming directly from the sun, it also absorbs radiation or takes in radiation from the circumsolar region, right? So here, alpha naught is the optical tolerance of the whatever instrument we are thinking about. That is usually between 0.6 degrees to anything to like 5 degrees, right? Alpha S is the extent of the sun, so it's about 0.65 degrees. And just to show you what the effect of circumsolar is, I prepared a little demo, which you can follow along on your phone if you want. So if you go to bit.ly/circumsolar, you can see. So this one right now here, this plot is showing the circumsolar normal irradiance, so the circumsolar component of the radiation against the angle from zenith. Yeah. So right now there's nothing, right? Because the aerosol optical depth is set as, actually, let me just refresh this. Yeah, right now it's nothing because the aerosol optical depth is set at 0, right? So there's no scatterer in the atmosphere, or very little. Yeah. Okay. So if we increase the amount of aerosol in the atmosphere, then now we can see the sort of the sun, what we call the sun shape, starting to emerge. It's mostly in the forward direction because of me scattering, so it's mostly in the forward regime. What else we can do? So we can change the wavelength. This is a spectral. Again, everything is about spectrally resolved calculation. So right now it's about 450 nanometer. We can increase the wavelength. Right. So as expected, for longer wavelength, the scattering is less because because of again me scattering. So the scattering is more pronounced when a wavelength is comparable with the size of the particles. Okay. So let's set it back to 450. Another thing we can do is the aperture half angle. So it's the alpha naught we're talking about, right? So how much we actually integrate through this region, right? So at 0.5 degree, the contribution from the circumsolar component is practically 0, right? But if we increase the aperture half angle, right? So for example, like a 2.5 degrees, which is the standard, right? So we are talking about almost 1%, and 2% if we go crazy. Another thing we can do is to change the aerosol type. So right now, it's plotting a continental clean type aerosol, which is fine, relatively fine aerosol types. We can go to a coarser type aerosol. So now you can see the circumsolar contribution also increases here. So now it's like 1.39%. And if we go to dust, desert dust, it's completely off the charts. So let's go back to continental clean with an aperture half angle of 2.5. Another thing we can change is the solar zenith angle. So that basically means how thick the atmosphere is. As we go to higher and higher solar zenith angle, the amount of radiation, the amount of circumsolar radiation decreases. The absolute amount decreases because the atmosphere is thicker, so the more absorption happening. But the percentage contribution increases because the direct beam is also attenuated as it travels through a thicker atmosphere. So just to show you what is the largest number you can get. So let's increase the solar zenith angle, go to the shortest wavelength, and let's do a desert dust, right? So in this case, we're talking about almost a 50% contribution. And if we don't account for the circumsolar factor, there can be, a 50% underestimation, albeit this is a relatively extreme case. So typically, it's about a couple percent contribution, again, depending on the wavelength you're looking at. Okay, so that is the circumsolar factor. And in practice, the calculation is quite computationally expensive. So we have a lookup table. So lookup table pre-computed by solar zenith angle, AOD, aerosol type, and wavelength. Right? So we can pick the right one depending on the combination of the parameters, right? Circumsolar factor, and then we can plug it into our previous scheme. Right? So we can just plug it into it, and that will represent our That will represent this this last scheme. Okay. Good. So those are the 4 schemes, and now let's take a look at how they actually compare against each other. And so let's look at the results. Right? So just to remind you, we began with the climatological aerosol approach. Right? So here we're plotting the simulation error in watt per meter square over an entire year at Santiago. So you can see there's a bias, there's quite a large spread. So the bias is approximately 43 watt per meter square if you just fit a Gaussian. Right? But what is 43 watt per meter square? Right? So it's easier to interpret things when things are in percentage. Right? So there's the same plot in percentage, and so the bias of a climatological approach, the baseline approach, is approximately 4.5%. Of bias. Again, so what is 4.5%? So 4.5, is that big or small, right? So let's do a quick back of the envelope calculation. So I've just quickly tallied up the world's largest photovoltaic stations. I mean, these are not multi-junction ones, but whatever. And the megawatt output over 20 years, which is a typical lifespan of solar cells. Assuming electricity in the UK costs about 13p per kilowatt hour, that's 47 billion over 20 years, right? So now we can make this axis into something more relatable, i.e. money. So in billions of pounds, right? So a 4.5% deviation represents about 2 to 3%, 2 to 3 billion pounds over 20 years. And just to give some perspective how much that means, so that basically pays for Jews. And it won't be a talk without a little train fact, so Crosswell is there. That does put things into perspective, doesn't it? Okay, anyways, get away, money, silly business. Okay, so let's go back to the percentage here. So 4%, a couple billion, right? So that's not good. Right? So going back to the percentage here, what I've done here is just plotted an error bar here. So this is plus or minus 3%, which is the uncertainty of the ground-based observation that we have for our validation. So that was the climatological aerosol scheme. And this one is when we have done the spectral aerosol classification. Right? So now instead of prescribing the aerosol type, now we're trying to classify it. And it does substantially improve both the mean and the bias of the distribution. And if we also do the optimization for the loading, so perturbing the amount of aerosol in the atmosphere, and now I don't know if you can see it properly. Yeah. So right now we're talking about under 1% of our deviation. And lastly, we're talking about the circumsolar factor, and this is the last thing that we added to our estimation scheme. And the ultimate number we got is for Santiago, is a 0.34% with a standard deviation of 3%. So that's pretty good. That's the bias is almost negated, and the spread of the distribution is quite close to the uncertainty of the instrument. Now, bearing in mind this is only testing for 1 year at Santiago, so it might be better or worse. But Santiago has quite a complex aerosol climatology, so we think this is quite representative of the scheme, of the merit of the scheme. Just to show you a few more plots. So we're talking about circumsolar factor here. So this is showing the distribution of error before we add the circumsolar factor and after we add the circumsolar factor, plotted against the zenith angle, right? So you can see, do this, yeah. So you can see before we added the circumsolar factor, there is more bias for higher Zoller zenith angle, and that has been reduced when we included the circumsolar contribution in our estimation scheme. Similarly for yeah, I think that's what I'm going to show. And similarly here, we're plotting the distribution of error for different types of aerosol. Previously, we can see that before adding circumsolar factor is after we adding the circumsolar factor. Before we add it, we can see kind of two distinct distribution depending, looking at fine aerosol or coarse aerosol. And by introducing the circumsolar factor, again, which is parameterized by the aerosol type, now we're kind of like getting a more aligned distribution, which is kind of showing, just to show that this is kind of doing what we expect. Right? Last plot I'm going to show here is there's some statistics about the spectral behavior that is generated by these different schemes. Right? So this is showing the mean and the standard deviation of the spectra that is predicted by each of these schemes, again, over an entire year. Right? So you can see the bottom line here is that depending on which scheme you use, right, you get quite different spectral behavior. And overplotted here are the quantum efficiency of a, again, typical triple junction solar cell. So you can see, depending on, if we did not include the circumsolar factor, if we didn't do, loading optimization and so on, right, we can get a very different estimate of the power generated by each of these layers in the semiconductor. So that's kind of the illustration of the scheme. So just to end, let me find the right brick. Okay, that's the right brick. Okay, so right now we are using aerosol measurements from Aeronet, so ground-based measurements. The ultimate goal is to be able to produce and run this Dni estimation worldwide. Right? So the idea is to use satellite measurements instead of ground-based measurements. And so I'm going to leave you with a model I've built of. Does anyone know what this satellite is? No, no guess. It's MVSat, which houses the AATSR, which is what we're gonna do next. So use aerosol that's retrieved by these satellites and just plug it into here. So literally swapping out the brick. Well, I'm not gonna do it, but yeah, literally swapping out the brick and see how it performs. Yeah, that's it.
Questions?
That's an interesting attempt.
So when you talk about aerosol size versus function parameter,
yes.
and you say it's related to the absorption. The absorption is independent of the dust size. So what about reflectance? Is that
Sorry?
The reflectance of the dust, is it also included in this absorption?
Reflectance.
Yeah, so I imagine bigger dust might reflect more than small dust because this would be more surface.
Yeah, so I mean, depends on what aerosol you have in the atmosphere. It will affect the albedo of the atmosphere. I mean, that plot I was showing there it's just the idea of that, to sort of qualitatively separate out different types of aerosol. You can kind of just do it by, two parameters. You can. I mean, I've seen people who've tried to classify aerosol with a lot more. So right now we're just classifying like a two-dimensional space, right? And that kind of separate out, the main types of aerosol. You can do it in, high dimension space. So absorptivity, single scattering albedo, what else? All sort of things, right? And there are people who try to cluster things in these multi-dimensional space to classify aerosols. And again, like. I think like this approach to classify aerosol, unlike the spectral one, which we're talking about, it's a little bit more hand wavy because you have to draw boundaries in these in this whatever space you're looking at, and it could be site specific, it could be specific to a climate climate. Yeah.
Tim,
Oh yeah, I was going to ask a question. So you threw away clouds quite early on.
Yes.
So today,
I don't know what it is.
the exception that proves the rule. In general, I would imagine clouds are quite important. If you're
They are.
worried about
They are quite
low
important.
energy output.
Yes.
So is that something that you, at some point, want to put into this one? I guess the goal of this is to try and work out what the right solar panels are for a particular environment.
Yeah, exactly. So yeah, so we need to account for cloud. But with clouds, they're much more diffuse irradiance,
But
right?
for example, I'm thinking clouds. The cloud fraction is a function of the time of day.
Yeah.
You
So
talked about
particularly
Fairbanks
for like
being important, for example.
yeah, so particularly for like very thin clouds, that those are the conditions, situations that we still need to consider. Right now, I'm quite aggressive in terms of my cloud screening because there's no mechanism to do with that for now. But in the future, that's something that needs to be accounted for. And the circumsolar factor, which we saw just now, it's actually clouds is very important. So if there's like thin, serious clouds, none of this aerosol thing matters anymore, right? That is the first order effect. Yeah.
Any other questions? Joe?
You're going to continue with your economic analysis and be able to produce advice to people in Santiago as to their advice on
So there are kind of two ultimate goals, right? So if we know the spectrum that we are expecting, right, there are two things we can do. First is, we have so for Santiago, if we sort of determine the typical climatological sort of spectrum that we expect, right, we can start to sort of engineer the semiconductor, the thickness, and the doping or whatever things that I don't really know too much about, but to optimize for that specific climate, right? And the other way to look at it is that if I have a particular design of solar cell, where should I target it? Where should I deploy it? Right? And that depends on the aerosol climatology and so on. Yeah. And yeah.
Okay. All right. I think we'll see you there. Thanks for watching.
It's a bit of a mess.
Now it's
I didn't manage to pass these around. I've been told I should pass these around.